Okay. We are got the technology happening here, and we're gonna talk about composite numerical integration. So last time we left off and we said that we had exactly the same issues come up that we did with polynomial interpolation, and that was the situation where we have some function on an interval a b, and we decide we want to integrate that function, and we had the idea we want to do the integral from a to b of f of x dx, and then we decided to interpolate with a single linear function. Then we're like, hey, we can do a single quadratic function like that, and it's over the whole interval, and then we can increase the degree of the polynomial, and we get the exact same problem. We get the Runge phenomena and the polynomial interpolation itself. There's errors in it. So then we have two ways of fixing that. We can have uneven node spacing, or we could have a different polynomial interpolation on each interval, right? So instead of having one trapezoid for the whole thing, we decided that, hey, maybe it's a good idea. Maybe it's a good idea to have a separate trapezoid in each region. This is the cubic spline idea. Yep.
So could we, because the interval, to reuse the traditional stuff.
So this guy has done something extremely clever, right? You realize, hey, we got better result in the numeric differentiation by applying that Richardson extrapolation. Quite a good little idea. Why don't we just do that here? And I'm saying that is exactly what we're going to do once we finish it. That it's going to be called Romberg integration, and it's going to be applying Richardson to the trapezoidal rule. Exactly right. Way to think. That is really good. I'm really happy to see you thinking about the tools that you have and going, hey, I can apply that to something I haven't seen it before. It's exactly what we can do. Nice job. Okay. Anybody else with a question? Okay, so here we are. We've decided now to either put one trapezoid or one quadratic function through each interval, and then add them all together. That's where we were at last time. And then we are going to just observe a few things that are going to allow us to say what the error bound is. Okay, so we got, if I'm taking a look at the fact that I've got a sum of a whole bunch, I've got a whole bunch of error terms. And I'm going to notice that if I have 1 over n times the sum from j equals 0 to n minus 1 of the third derivative of these functions at some number, which we don't know, that this guy is bounded. It is bounded by the maximum value x in AB. So we're going to say we can say it is some exact thing, but since we don't know how to figure out what that is, we're going to say, okay, let's find out where the third derivative is maximum on the interval. It can't be any worse than that. And so that is here. I'm writing that as the maximum value of x in AB of the third derivative of x. Okay. We got n of them. Okay, and also it is the case that we have a minimum value which we can identify, and that is going to unsurprisingly be this thing here. This guy will always be greater than or equal the minimum if I choose x, some number in the interval, and I bound the third derivative. So we've got actually a lower bound and an upper bound on this guy right here. This right here, we've got an upper and a lower bound. So we've got 1 over n, which is write that out here. We've got a upper bound. And we've got a lower bound. Right. Okay, and this is actually the intermediate values here, or intermediate values here. Tells you that there is gonna be some mu in there where. So intermediate values has there and tells you of that guy is going to be equal to the third derivative of mu, there's some mu in there. I don't know what that is. Okay, so what do we get? We get that our integral from a to b of f of x dx, the thing we're trying to calculate, is going to be h over 2. This is our composite trapezoidal rule. From j equals 0 to n minus 1. And what do we have? We have the trapezoid in each interval. That. And then we have this guy here, h cubed. And over 12, we're about to see that error bound in Stewart textbook. And mu is in AB. Okay, so we have h, if we have equal space, interval that we're dividing up, that then the equal spacing distance will be e minus a over n. And that of course means that nh is equal to b minus a. Okay, and then we get the composite trapezoidal rule. Here it is. A to b. So this is what you've seen, possibly with slightly different notation. In the Stewart textbook. And then we have this thing over here, the actual error term, which is b minus a over 12 h squared times c. Found on the derivative. So it is a whole h squared method. That is the composite trapezoidal. So it's all about, in this case, starting with the Lagrange interpolating polynomial, and then keeping the error term for that, and then working through how you can replace, you use a linear Lagrange interpolating polynomial, keeping the error term for that, and just work through what's happening, adding them all up. You derive the trapezoidal rule, and you also can get a bound error. The main message is that rather than using one polynomial over the whole interval, we're going to use a low degree polynomial, many different ones over the interval. Okay, and we could do exactly the same thing. Not going to go through the derivation, but we can do exactly the same thing for the composite Simpson rule. We can do the same thing again for the composite midpoint rule. Okay, let's just actually make it, we haven't done this yet. Let's make an example of actually just using this thing, just to recall how to do this. I know that you guys have done this before, but let's take an example. What function did I use? I'm going to say, let's use 4 intervals, n equals 4. And we're going to approximate this integral from 0 to 4 of sine x dx. Now, I'm just going to here put the exact value, This is not from the approximation, so I can see how I'm doing. 6, 5, 3, 6, 4, 3, 6, 2. Okay, so we're gonna try to make an approximation of this, the trapezoidal rule. So, trapezoidal rule, our H is gonna be, B minus A over N. B minus A over N. And so each one of our subintervals is going to be of this one. And so if I use the trapezoidal rule, I'm gonna estimate this guy, here it is, sine x dx. I'm gonna estimate that to be 1/2. That is H over 2. And then I'm gonna take the sine of 0 plus 2 times the sine of 1 plus 2 times the sine of 2 plus 2 times the sine of 3 plus the sine of 4. That is how you do it. And you get some number, and that number in this case is 1.5 times 3. That's just a be called that by. It's pretty easy to figure this out. I mean, if you can't remember that there's just those 1, 2, 2, 2, 1 like that, then what you do is just draw the little, draw the function, that the whole. They have some function, and you're here. This is f at a. Yeah, this is f at a. This is a. A. This is b. This is f at a. And this is f at a. Okay, you have, if you had to divide it into 4 like that, you'd be thinking, okay, how do I calculate it? If I can't remember the formula, you're like, oh, I'm calculating this calculator. You figure out what that is, you know what this is A plus H. And then you're like, okay, I figured out the area of that. And then I can see what's happening. I'm using f at a, calculate this one, and f is a plus H. And then when I do the next one, I'm using that value again. So I'm using this value twice. The endpoint I use one stop is there. Okay. That is trapezoidal rule. Any questions about that? Okay, let's do Simpson on the same thing. How to actually use this stuff. So on the Simpson's rule, we're gonna have that the integral 0 to 4 of sine x dx is going to be equal to 1/3. So this is still with n equals 4. This right here now is h over 3. And we are going to be taking the sine of 0 plus 2 sine of 2 plus 4 sine of 1 plus 4 sine of 3 plus sine of 4. And I get that guy out of there, and it's 1.6645. It's better. Simpson rule is better. It's a higher degree. I don't know. It's really bigger, and it's not that big. It's not that you went up down to 10. Not it's all small, and there's lots of them. The fact that this is a degree 2 approximation to the function over the interval, because degree 1, it makes it better. So, okay, the Simpson method is OH4. We went through that. Trapezoidal is OH2. It's Simpson better. Actually, the Simpson method is one of the most frequently used so does that. Okay, let's take a look at some pictures. I'm just going to compare these two things. I got a picture here. There is some code on the Canvas page you can download and run. But let's just say we want to approximate this ugly looking thing here with integral here. And we do it with the trapezoid rule and the Simpson's rule. You can see this is a graph of the error, log of the error versus log of n. And this, trapezoidal rule, there's the trapezoidal rule there. What is that slope? You think? What would I expect to see there? Huh? -2, yep, for sure. Slope is -2. That's right, it's an OH squared method, going to 0 as H gets small. Okay, and here's, you can see it, and here is Simpson's method on the same function, and what is the slope there? Huh? Slope is, oh, -4, yeah. Okay. We're getting down. This in this case, the Simpson's method, we're with this many iterations, we're down to basically machine epsilon, and this one may have continued, it may well continue down. Can't tell. But there's no reason to expect it not to, right? If you're gonna continue down, you can get down to machine epsilon. You've got to do a lot of intervals. Like, look at this, already 10,000 intervals on the Simpson method, and it's noticeably more on the trapezoidal. Okay. So Simpson's, in this case, Simpson's rule, we got 15 digits of accuracy. So basically, machine epsilon with n equals 10,000. That is a lot of function evaluation, especially when your function is relatively complex, like this guy. You got to calculate that function at 10,000 different points. It's however, roll off, round off there. You don't have that problem like we did with the numerical differentiation. You don't have that problem where you can kind of get better and that's it. It takes it off and starts getting worse. It is robust and it is also inefficient. Those are kind of two main methods. I guess three main methods. We've got the trapezoidal rule, the Simpson's rule, those are closed using post methods, and we have a midpoint, which is an open post method. Let's contrast MATLAB quad command. Okay, so if we're in MATLAB here, so we have some function, and then we say fly a quadrature routine and evaluate. We get these things out. We ask God that is the quad command, which does numerical quadrature, and you pass it the function, and you pass it the interval over which you wish to approximate. You'll get an approximation value, and you could also ask MATLAB how many function evaluations you have to do. Okay. So in this, if you enter that function that we just had, and you enter A equals 0 and B equals 1, and use the MATLAB quad command, and you ask for an approximation that you get here for the integral, and ask it how many function evaluations did you need to do at when that number that you have there is equal to 117. That's a lot less than 10,000 error. That you then you can calculate the error. That the error was already down to 10 to the minus 8. Okay, so how come that not doing that and then it's really not using or something that do that? And the idea is to use adaptive quadrature. Then this is also no okay, and what is the first part of this? Okay, so adaptive quadrature. We're gonna notice that in the little graph that we do there, that we are able to use the integral robustly by using a large number of calculations and the size, subdivisions. So these composite integration rules have this very nice feature that the round off error does not increase with the number of calculations that's done. Why is that? Let's talk about that. Illuminate ourselves on why that is. Okay, so let us just say we've got a function evaluation, f at xi, and we approximate that. This is the round off error. In finite precision, right? We make a function evaluation in finite precision. We don't get exactly the value of the function at xi. We get something small difference. Where the case where we're thinking is that the function is value, the exact value is this approximation that we get when we actually do this on a computer plus some. Okay, and then we're gonna do that in each interval. So, at each node that we make this, at each addition that we make, each factor that we make to the function evaluation, we're gonna get the approximate value that has a small amount of error in it. And so I is here going to to n. And then this is equal to the round off error. Let's see what happens then. Let's take a look at the trapezoidal rule. What is the total round off error? Take a look. Trapezoidal error. Trapezoidal rule. Total round off error. This is not the error from truncating the polynomial. This is the first round off error. So that error is going to be h over 2 times the error in the first function evaluation plus 2 times the error in all the function evaluations for the, because we have to double the ones in the middle and then the one at the end. Okay, we're going to have error on each one of those. We're going to add them all up. That is going to be less than or equal to this guy here. And I'm going to put absolute value signs on it. So some of the errors might be a little bit more. Actually cancel out. But if I take the absolute value of all of them, then I for sure get a 5. Right? That's what I'm just doing here. Right. Now, let's take an upper bound on all these guys. Each one of these calculation errors is going to be less than or equal to some bigger number. That's the maximum of that. Okay, then that allows me to add these things together. So that means that the error is going to be h over 2. So this guy is going to be epsilon, and that's going to be 2 times 2. 1 and epsilon plus epsilon. I can add those together, and that is n h epsilon. Okay. N times h is b minus a. Right? That's how we picked our space of h. We took the size of the interval and we divided it into n. So that means that the error here is less than or equal to United States. Right? So check this out. That is independent of the number of calculations. That's why it's robust. But not that way. Okay, main point. And so now we want to try to do something a little bit better. And we're going to take the suggestion of the gentleman here, and we are going to do a Richardson approximation, extrapolation procedure to do better with less calculation. Okay, let's see how that goes. This is called Romberg integration. There it is. Romberg integration is applying Richardson extrapolation to the opposite propagator. Okay, this is going to be method one of trying to fix the problem. Method two is going to be mathematical. Okay, so here we have where we're calling what the trapezoidal rule looks like. There it is. This guy right here, this portion right here, that is your approximation term. This is on, and then we've got our interval divided into n pieces, and then this guy here is that is the consequent trapezoidal rule. We're right there. Okay, we're not going to do this, but it is possible. Leaving this thing alone, this is still the approximation here. It is possible to show that this type of error is of this form. So it's not that the error has changed, it's just to say, I can take this and show that the error is of this form. Why is this important? Why does it matter if it's of this form or not? Can we? Exactly, right? So it has to be, once we get an error of this form, that looks like this, and then now we're like, yay, we can use Richardson's extrapolation. So we're gonna do that. Right here we've got, we're gonna have, n is gonna be to k, k like that, okay? And what we're gonna do is we're going to make, we're gonna make an estimate. I'm gonna do it for the general situation. We're gonna like, so k is gonna be 1 to start, and we're gonna make our first approximation. It's gonna look like this. Okay, we're gonna go through, making, trapezoidal rule approximation. And we're gonna label them in this manner. And what we're gonna do is start with one, interval, and then we're gonna double the number of intervals each time. So, I would not expect you to remember this, but let's just then say, what is our Richardson extrapolation? This is when we combine stuff, when we combine it, it looks like this. We had this listed in the lecture on matrix and extrapolation. Looks like that. Let's do it. Like that. So this is the situation we have, three minus one. We have a situation where, we don't have, this is, it's not before, we don't have page square, page four, that's why this is four and that is two. Okay, and K will be equal to J plus that. All we're doing is revisiting the interesting extrapolation, general trends, and applying it to the extrapolation. Okay, there's two things that are going to happen here. That we can also, while we're doing this, we can reduce the amount of calculations in order to find these initial values. So when these are all one, these are our first one, and we start combining the second from the extrapolation. But we want to minimize the number of calculations. And when you take a look at what's happening, you realize that when you calculate this guy here, some of the calculations here have already been done over here. So you shouldn't redo them. Okay, so let's just write out what this looks like. This guy, R11. That is your most basic trapezioid rule right there. Right, one interval. This is the trapezioid rule of the whole interval. Like that. Then your next one is R21. Let's see what that looks like. That looks like so that looks like this, H2 over 2. What is H2? H2 is going to be H1 over 2. So now we're doubling the number of intervals, and we're going to calculate F of A plus F of B plus, I just reordered them slightly from what you just wrote to that. That's H over 2. Okay, that would be our that we started to make this one interval. Now we're going to make this one. This is what we do with letting up from this extrapolation. We have the number. Okay, but while we're writing this out, we will notice that we've already made this calculation and we've already made this calculation. Yeah. So we're not going to make those again. So in fact, I can write out our 2-1 as 1/2 of our 1/1 plus H1 times F A plus. So I make the approximation of the whole interval, and then in making the approximation over 2 intervals, I merely need to make only one more function evaluation, not 3 more. That's a big difference. So you just consider this, you just write this out in a general form that we're going to make all of these calculations first have 1 interval, then have 2 intervals, then have 4 intervals, then have 8 intervals. And we will do it by recursively using the ones we've calculated before to gain in efficiency. Where HK is so having the size of the interval and doubling the time, doubling the number of intervals. So now we've got all of our what we were previously calling N1 before. Okay, and we're calculating it efficiently. This reduces the calculation, that changes here, the bottom. Slide backwards here. Okay, now we're ready. We made all of these calculations. We're ready to apply the Richardson extrapolation. We're gonna do it exactly the same manner. What we have, we've just completed this column of the table right here. That is our OH squared trapezoidal rule approximation. And then so this was done here. This was done efficiently. It was done efficiently as per the previous thing, not repeating calculations like before. And then we apply the Richardson extrapolation, and we use these two guys to calculate that guy, and we use these two guys to calculate this guy, like that. Richardson extrapolation, we use those two to calculate this, etc. And each time we do that, we get a gain in the speed with which this thing will convert. It goes from OH squared, thanks to that OH to the 4 to OH to the 6, etc. So it's much more efficient. Okay, so that's the idea. So let's check this out. Here's a graph. We have our original trapezoidal rule. We have the Vetter-Simpson's rule. And then on this green thing here, we've got trapezoidal rule with the Richardson extrapolation, which we now call the Romberg method. And you can see how much better this is. I am now here at 100 function evaluation in order to do this, to get the same level of accuracy, which even for Simpson's method was 10,000. That's huge. Faster, right? Oh, so that depends on how many levels of the Romberg of the Richardson extrapolation you did. And so depending on that value, the maximum value, you're gonna get this. Okay. However, one thing to be aware of is that for some types of functions, you don't get the hoped for gain. You see here, we've got the trapezoidal, we've got the Simpson, and then we've got our Romberg. Let me just draw a line here. Not, we didn't, in fact, we didn't really get much of anything out of it. Okay, so when we have, ugly functions, and what does it mean ugly? Sometimes we don't get the anticipated gain. And what ugly means here is we're doing this, like this, and in order for the Richardson extrapolation to work, we're thinking, okay, this is what we're doing, H/2. This is our trapezoidal rule. And we have this 2 times the sum, n minus 1, okay, and then we have the endpoint like that. We have that, and then we have this K1 H squared plus K2 H squared plus dot. And we relied on this one in order to be able to use the Richardson extrapolation. And these constants here, we didn't explain this. We didn't sort of go through the derivation how this comes up. But those constants there depend on the derivative of the function. So if the derivatives are large, then those numbers are big, and then these are the derivatives are. So that's what the statement is saying at the bottom here. Romberg integration may fail when the function is not smooth. It's a formula of, being on hold. So there are sort of more cautious, algorithms, and you take a little bit more intelligence into your brain, to try to mitigate against that kind of a problem. And the key idea here is gonna be this idea of adaptive logic. Which means we're gonna move the node to where the function is changing fast. What you guys are doing when you're computing with them. Right? You have a question in the back? No, stretching in the back. Okay, question. Okay, let's take a look, how much time we have here. Let's just take a quick look at the adaptive register. It's not, the idea is, I think, pretty straightforward. Maybe alive at the end of the lecture. I hope so. I am also actually not feeling well. It's possible I might actually have to cancel my office. I kept that. Not good for the results. Okay, so here we are, adaptive register. Okay, so we have just been coming along this whole time, basically taking equally spaced nodes. Now, you can imagine here, we have a function that maybe looks like this. And we're trying to find out what the area under here is. And we are thinking of basically interpolating with a polynomial. Where should we put more nodes? Rather than equally spacing them, where do you think you can put more? Huh? Go ahead, Brian. You can put the nodes at the root, but okay, that's right, right? I mean, this is our computing assignment. We decide to kind of put the nodes like this, right? And of course, that means we have a lot more nodes where the function is changing quickly. So the idea here is we want more nodes here. More nodes here and less here. So on the computing assignment, you have a flavor of the adaptive quadrature, which says you want to integrate a function. And then what are you doing? You're going to say, okay, I'm going to do a bunch of different integrals. And I'm going to integrate like here and here and here and here and here and here and then here. In pieces like that. Okay, because it's a bad idea. It's a bad idea to pick them equally, because what happens is, let's just say you pick them equally, like here, here, here. Like, okay, but here, now we're gonna be in a situation where we, like, let's just take these two nodes. You can say, okay, what is the value of the function there? There. What is the value of the function there? We're gonna then, there. We're gonna approximate like that. That is not gonna go well, right? Because the function is fluctuating so much. It would be easy, for example, to interpolate here, like this, and just say, here, just like that. It doesn't, right? It's changing very frequently. So you need to get more nodes in there in order to capture that. So that's the idea of the adaptive register. Put more nodes where the thing is changing a lot and less where it is not. You cannot use adaptive register if you only know f of x is in a fixed set of nodes, okay? You just note that down. You only know the function of a fixed set of nodes. Those are the ones you're using. Right there, at the end of the game. So if you have the ability to place the nodes where you want, then you want to use an adaptive register algorithm to place the nodes. And what you want to do is place the nodes so that you have sufficient numbers of calculations, and you also want to do that automatically. You're going to have to intervene with some sort of intelligence to understand how to specify the nodes. So I think I'm going to stop here, and then when we come back next time, we'll have we'll go through an adaptive method of placing notes based on distance learning. Okay, I will see you guys on Wednesday.